Welcome to the 11th Geopolymer Camp. It is now a well-established tradition that I present what I call the state of the geopolymer research and development. I do each year a selection of interesting scientific papers, patents, or events which happened or were published since the last Geopolymer Camp. First part, it is the 40th anniversary of the foundation of the Geopolymer Institute. Second part, ancient geopolymers in South American monuments. Three part, regular research and development, Geopolymer Science, technologies, low CO2 cement and concrete. We are celebrating the 40th anniversary of the creation of the Institut Geopolymer, Geopolymer Institute. When did this research started and why? It started in 1972. A lot of you are aware of this slide, but I repeat and I repeat it. We had in the 1970s in France a terrific fire in a nightclub where 150 young people died because of the flames and the emission of plastic furniture and plastic decorations. I was an organic polymer chemist at that time, working here in Saint-Quentin on textile fibers. And it was a shock for us, it was a shock for the industry. So I raised the questions, plastics are dangerous, are organic polymer heat and resistant? For me, it was obvious that nature was stating no, only minerals are providing fire and heat resistance. So I set my target in 1972, create mineral polymers to solve this problem. And we created a private research company here in Saint-Quentin with our textile industry partners, which was located not far from here, 300 meters, in this building that was an ancient and closed textile laboratory. This building no longer exists. It has been destroyed and replaced by regular apartments and buildings. And this is how it looks like in the entrance. Everything is still in French at that time, and we were presenting our first applications. This was in 1972, and 4 years later, after the creations, I made my first scientific paper at a conference in Stockholm. It was a UPAC symposium on long-term properties of polymers and polymeric material. The title was Solid Phase Synthesis of a Mineral Block Polymer by Low Temperature Polycondensation of Aluminosilicate Polymers. Strange jargon. In my company, Cordy. This paper is in our library, Geopolymer library, and it has been downloaded more than 2,300 times. And then I officially introduced the geopolymer terminology later in 1979, January in the US, at a plastic technology development organized by the Society of the Plastic Engineers. My target was always fire resistance. And the title, Synthesis of New High Temperature Geopolymers for Reinforced Plastic Composite. And I introduced the geopolymer terminology. Polysilate, SiL1, the geopolymer terminology is governed by the ratios Si, silicon to aluminum, polysilate, SiL2, we have two Si for one Al, SiAl3, 3Si41Al, and for SiAl higher than 3, silate link. So you understand that I totally made the transfer from organic polymer chemistry into this new geopolymer chemistry. And this is why this terminology had to be created. Then we feel that it was time to create a scientific institution. And this is a copy of the official journal of the French government, 26 May of 1979. It is the foundation of the Institut de recherche sur les géopolymères et leurs applications, Geopolymer Institute, Research Institute on Geopolymers and their applications, with a mission, advancement of knowledge concerning geopolymers, teaching, dissemination, application of this knowledge in the technical and natural sciences, humanities, arts, literature, as well as the exploitation of the general resources. Head office in our company. For what applications that have been developed? Fire and heat resistance, cement and concrete, global warming CO2 emission. I have been involved in global warming CO2 emission since 1990. That's 30 years ago when we started at Pennsylvania State University a project. We asked for funding from the EPA. This had been declined. So when I came back to France, we started alone and we started with European partners. Environmental technologies, because the geopolymer binders and geopolymer structures is the ideal material for containing toxic, chemical toxic waste and radioactive waste. This has been done. And archaeological sciences. Our first international conference was held later, 1980. 9 years later, it was in Compiègne. Then 11 years later, the second one. So you see the time between each conferences was really very long, and since in fact, we were more interested in developing products than publishing and doing scientific papers. The second was in 2002 with the Melbourne University members. Then our International Geopolymer Congress in France, here in Saint-Quentin, not at this place, but in other place, and in Perth, in Australia, in 2005. And in 2009, our first Geopolymer Camp in Saint-Quentin. And since that, there are international events that are organized by others. And it's just my participation here. I am just showing that we have been asked to start a Geopolymer Camp in Africa. We have always problem for people wanting to get visa, and sometimes they are declined, and a lot of African and from other countries have problems to visit, and maybe this is the place to organize such gathering, and this is within the International Conference on Advanced Material near Tunis. But it is also the 10th anniversary of Geopolymer Camp. And we have, from each camp, the keynotes and the videos, my keynotes and the keynotes of the major speakers that participated, that are available on the internet. So the first one, 2009, was dedicated to mass production of geopolymer cement. This is a video that has been watched more than 14,000 times. For scientific videos, I guess it is a lot. In 2010, we had a lot of news on archaeology. I will have a description later, come back. In 2011, but it was the introduction of what we call the synthetic metakaolin. So relying on synthesis based on salt gel, we get metakaolin. In 2012, it was the first opposition between cement chemistry terminology and geopolymer terminology. This is connected with my fights against alkali activation, alkali activated material. In 2013, I started the first webinars on the internet. And we had also space applications, geopolymer carbon fiber composite. So these are the slides and what you get in my keynotes. In 2014, I have, which is part of my keynote, was what became the part one of my series, Why Alkali Activated Materials Are Not Geopolymer. And then we have the first public building made out of geopolymer concrete. A public building, not a small private thing just for fun in my garden. Public building. At the University of Queensland's Global Change Institute, all the ceilings have been made out of geopolymer, precast slabs. In 2015, we had the introduction of 3D printing from small to big, and Wagner's Well Camp Airport. So we had minute 20 millimeter scale application up to 100,000 tons application. This is the range of applications we are involved in. 2016 was dedicated to show my visit to Brisbane buildings and to Toowoomba Airport. In 2017, I was, for a second time, shocked by a fire. It is the London fire. I have in my book, chapter 22, dedicated to fire and heat-resistant geopolymer foam. We had a German company, a big company, licensees, that created a startup company in 1987 that was called Trollit to promote this type of materials. And after 5 years, they closed the plant because it was too expensive for the market. June 14, 2017, 30 years later, this is reality. We are doing our job as scientists, but in fact people don't care. This is, economics is governing the world, and this is the problem with CO2 emission, fire resistance. We have all the solutions, but they are not applied, or we cannot apply them, or we don't have the finance, the funding to do it. There are only small individuals, entrepreneurs that are doing things. So this shows the evolution of the society. So I come back to my keynote from 2010 that was strongly dedicated to archaeology. We had in the newspaper, this is the Boston Globe papers, and it was also in the New York Times, a new angle on pyramids. Scientists explore whether Egyptians used concrete. These scientists are from the MIT. MIT students, under the direction of Professor Lynn Hopes, are building a scale model to test a contrarian theory, and this is how the Egyptian government responded to the scientists from the MIT. Zahi Hawass, head of Egypt's Supreme Council of Antiquities, minced no words in assailing the concrete idea. It's highly stupid, he said via a spokesman. The pyramids are made from solid blocks of quarried limestone. To suggest otherwise is idiotic and insulting. So all my scientific colleagues and myself have been treated idiots since 1984 by the Egyptian authorities that doesn't want to have this knowledge applied to their pyramids, because by applying them, we no longer need all the 100,000 slaves, and for them, the 100,000 slaves is important for their mass tourism. When you go to Egypt, when you go to the pyramid, you see the flow of tourism coming and coming and coming and coming and wondering, the poor slaves that were involved in that. So this is the situation. It is very, very, very difficult to have to convince these authorities, and especially the Egyptian one. But we also made a discovery. We discovered the oldest geopolymer artifact, 25 years old. It is the Venus from Dolní Vestovnice. It is a small item made out of ceramic that is located at the Brno Anthropology Museum. When I saw it for the first time, I said, oh, I know how to do it. We had worked on a similar system in our lab. This is what I call low temperature geopolymeric setting with clays. And so we have replicated the Venus of Dolní Vestovnice. We took clays, we had a replica from the Venus, clays and 1% Na2O, had the Venuses dry on a garden fire, then put it on the smoke, no flames, and we got our black ceramic made in a simple fire. But this is only possible if you have the right minerals, the right mineralogy, the right clay, and if you are adding to the system the right chemicals. And these chemicals are, in fact, included in the ashes of the plants that were surrounding these people, and the Dolní Vestovnice small statue contains remains of these ashes, which proves that they used this technology. 25,000 years old. It is low-tech, but it is working, and it shows you the long-term durability of the geopolymer chemistry. After this historical review, let us come now to the present time. The state of the Geopolymer R&D comprises usually 4 parts: Geopolymer Science, Geopolymer Technologies, Geopolymer Cement and Concrete, Geopolymer and Archeology. But today, I'll change the order. We'll start with Geopolymer and Archeology, then we get Geopolymer Technologies, Geopolymer Science, and Geopolymer Cement and Concrete. I already presented last year discovery on ancient geopolymer in South American monuments. I will just repeat here in a summary of my presentation that is also scheduled for this afternoon in the special session. What we are dealing with, this is the Altiplano in South America. You have Cusco in Peru, you have Bolivia, and the Lake Titicaca. We are at 3,800 meters above sea level, and we are talking about Tiwanaku and Pumapunku. Tiwanaku is well known because of its sun gate that is in volcanic rock. But close to Tiwanaku, there's a site of Pumapunku that is made of huge megalithic red sandstone. And we discovered by looking at this site that these people in 600 AD, that is 1400 years earlier, used two different methods to make artificial stone. For red sandstone megaliths, a geopolymer in alkaline medium, and for gray sandstone structure, a geopolymer in acidic medium. The first one, Pumapunku red megalith, so we have terracer blocks, 130 tons, 8 meters by 8 meters. Number two, 180 tons, these are monoliths that are broken. Number three is blocks, parts are vanished. And number four, 150 tons. And it has been told by archaeology that the people were carrying these huge blocks, a house as big as a private house, down from the mountains on small llama caravans. This is idiotic from our point of view. The result of our study was published in Materials letter under the title Ancient Geopolymer in South American Monument, SEM and Petrographic Evidence. It was online on the 8th October 2018 and published officially January 2019. We come back this afternoon to that paper. This has been dedicated only to the big monolithic sandstone geopolymer stone. What we found was the following. If we compare the thin section under the optical microscope, this on the polarized light, we see here, this is the geological sample, that we have quartz, we have feldspars and so forth, and from time to time we have small amount of clay, very small, and so forth. This is sandstone, regular, natural. Pumapunku monuments, what you see, you have very thick matrices around pockets, islands, and these are geopolymer, red sandstone, ferrosilate geopolymer. The second method is dealing with andesite, volcanic rock, totally different systems, but used in incredible artifacts. These are the so-called H artifacts. They are sculpted in such a minute way that it is impossible to replicate with what the tools that they had supposedly at that time. They were 1 meter high. It is andesite, volcanic stone, very hard, like quartz, most hardness 6 to 7, impossible to carve, impossible to sculpt. And we published our results in Ceramics International. Why not in Materials letter, like the first one, because Materials later has a policy they do not publish twice on the same object, on the same subject. It was a different chemistry, but for them it was accepted that the stones were artificial, so we had to find another friendly publisher in order to get ancient organo-mineral geopolymer in South American monuments, organic matter in andesite stone. What do we found? This is a point under the optical microscope. We studied on the surface. This is plagioclase, volcanic, and we found here something strange inside. And this is under the SEM. We have plagioclase, play, hornblende, pyroxene augite. These are well-known crystals. And here we have something that looks amorphous. And we focus on this amorphous thing. And under EDS, we find a lot of carbon. We found nitrogen and then minerals. So it was organic matter. And organic matter in a supposed volcanic rock. This is impossible. And we'll see the demonstration. We'll have this explanation in our Geopolymer Institute site. There are a special page on it with all features, with all pictures and explanations. But it generated a lot of buzz on the internet. The first one was a French blogger that just took the 7 last minutes of my keynote when I was talking about these organic matter, and he immediately made a video on YouTube, and it has been watched more than 130,000 times. But more, in March this year, 2 or 3 months ago, on YouTube we had also a group that are called the Ancient Architects that made a video that was watched, that is watched continuously more than 268,000 times. And in this video, that is short, 14 minutes, they copied the entire article on the making of the volcanic stone. So you have scientific papers that have been watched on the internet more than 2,600 times. A scientific paper. And it is obvious that it's now the most downloaded ceramic international articles because of that. So let's come back to technologies. What we have, we're not talking of making a geopolymer, we are always talking of making a product. That is a geopolymer binder, a geopolymer resin, or a geopolymer paint, or a geopolymer coating, or geopolymer grout, or geopolymer foam, or geopolymer cement, or geopolymer concrete, or geopolymer carbon composite, or a geopolymer ceramics. And this is governed by the SIAL ratio. I plot here low-tech, high-tech, and here the networks, the molecular structure that we get. We start with SIAL1 and SIAL2. We have a 3-dimensional network, very rigid, and by adding more silicon, we enter into a more polymeric character that has less compressive strength but more flexible strength. And we have cement applications, toolings for the industries, high-tech tooling, and high-tech fire and heat resistant carbon geopolymer composite for cabin safety and racing cars. So this is here the start of the application. We have a list of practically 30 commercial applications. Some of them are only on the pilot stage. Some are really industrialized and commercialized. And I'll just present them briefly without any comments, just reading what we have. BASF Germany, PCI, Geofug, Geopolymer grout and binder. Milliken Infrastructure, Geopolymer mortar, system and grout for use in rehabilitations. ASK Chemical, Eichland, Germany, inorganic binding system, Geopolymer binder for foundry. Wagner's Australia, earth-friendly concrete, fly ash slag, Geopolymer concrete for infrastructures. Pyramidal System France, high-tech, high-temperature structural Geopolymer composite materials for automotive aircraft industries. Air Composite Ireland, heated Geopolymer composite tooling for manufacture of large composite structure for aerospace and windmill energy. Airbus France aircraft conduit in Geopolymer carbon composite. Schlumberger France, this is very important development, pumpable Geopolymer formulation for oil field application. Rockwool, Australia, Geopolymer rockwool briquettes used to recycle unused fibers. The French atomic energy method of preparing controlled porosity Geopolymer for catalysis and filtration. Scorburn, Germany, this is a very interesting application. Fireproof condensing chimney for hot gas exhaust made of Geopolymer foam. Panels in Singapore, precast Geopolymer panels. This is an industrial commercialized product from China, Nucor Geopolymer fireproof composite panels. From Russia, our friends will present it, 3D printer for buildings. Corning USA patent Geopolymer ceramic composite for high temperatures. Dow Chemical Geopolymer coating for organic polymer substrates. Sweden composition for sustained drag delivery comprising Geopolymer binder. Germany fire-resistant Geopolymer paint. Germany very resistant and acid-proof rigid anti-corrosive Geopolymer coating for the protection of surface on metallic and mineral bases. Czech Republic Geopolymer sand binder for cores in foundries. Netherlands Geopolymer composite siding and facade cladding. USA Nanovoltae nanoporous Geopolymer composite for use in water treatment as an absorbent for the removal of arsenic. Allied foam tech top Geopolymer foam, cement for lightweight and fireproof applications. Werner, ready-to-use alkali silicate for geopolymers. Vodisclo, Czech Geopolymer binder system for foundries. And Canada, Eoncrete Geopolymer concrete made out of mine tailings. Argue Belgium bricks, LTGS brick at low temperature geopolymeric setting. Pipes, Australia Geopolymer concrete pipes. USA watershed materials, high strength masonry with a low carbon footprint. USA Bowers Geopolymer concrete for acid resistant application. Finland's solution for water purification with patented Geopolymer nitrogen removal absorbent. This is important and it is working. Specialized Geopolymer technique for encapsulating various radioactive waste streams. They are guests now using it in Fukushima in Japan. Lucideon, same topic, encapsulation, immobilization of high hazard nuclear and chemical waste. Wincred, Brazil, decorative architectural Geopolymer binder panels for inside and outside, and geobiology applications. So this is just a small survey of what is done outside of concrete. Third part, Geopolymer Science. It is interesting to show how it was at the beginning. Our first conference in 1988, we had 1, 2, 3, 4, 5, 6 laboratories that started to work with us. And this is what we have today. It is obvious that from publishing scientific papers point of view, it followed the same trend, starting at 1 or 2 per year. This is my reference, 1991. And then we stopped counting. It's no longer interesting to show. In 2008, I was asked to present a roadmap for research and development at the Second International Congress on Ceramics, and I established a list of 16 research topics that are interesting to study separately. First, demonstrate the polymeric character of geopolymers. This is to fight against all those that are claiming that it is a single hydrate and nothing else. It is a polymer. Second, study the polysiloxanate. These are the soluble silicate, or jargon water glass. 3, metakaolin MK750 based geopolymer. In blue are those topics that I will focus on here, now, today. Calcium based geopolymer, rock based geopolymer, silicate based geopolymer, fly ash based geopolymer, phosphate based geopolymer, organic mineral geopolymer, long-term durability will be focused, geopolymer fiber composites, geopolymer and ceramic processing, manufacture of geopolymer cements, geopolymer concrete, materials for radioactive waste particles and gas pollution, and 16, 3D printing. Let's start with the polymeric character of geopolymers. This is my chapter 2. Geopolymer technology is well established. It is time to come back to the fundamentals. And these fundamentals are to be found at our Geopolymer Institute site, where we have, as I told you, videos from my keynotes and videos from those experts and scientists who presented their special findings. Then we have videos on my webinars, 12 videos that explains everything step by step. And then the series on why alkali activated materials are not geopolymer. We have 4 videos on this matter. This series, the number 1, has been downloaded at the Geopolymer Institute more than 17,000 times. And it is now on YouTube. We put it later on YouTube, but it is practically approaching the 10,000 times. When you go to Google Scholar in order to see what is happening with the publications that I've been writing since the beginning, this is what you find. You find here geopolymer inorganic polymeric new materials cited more than 2,600 times. This is the paper that is the most cited in the scientific literature dealing with geopolymers and the like. And the citations are continuing, containing more than 11,000 citations. This is, yeah. You get free download of a lot of technical papers that explains what you have to understand and to learn. Just go to the library and look at the technical papers, and we have also the archaeological papers. Number 3 topic, metakaolin MK750. 750 means calcinations at 750 degrees C, based geopolymer. I will be presenting later this morning in the sections creating standards for geopolymer. A study that has been undertaken here at the universities, standardized method in testing commercial metakaolins for geopolymer formulation. I will develop it here just briefly. So we developed from the beginning, since the beginning of our study, we developed a reactivity test in order to understand what we were doing. Very simple. This is a thermocouple, two testing samples. One is the reference, and one is the material that will be tested. And we make a simple measure of the temperature that we get when we put them in the oven. Depending on the temperature, you achieve exothermicity at 110. At 60 degrees C, you reached more than 140 degrees C, and so forth. Based on the different metakaolins, what we get for the testing of commercial metakaolins is the following. We follow here the time of curing, and here the temperature that we measure, and you see that all are different in terms of reactivity. We'll come back and we'll explain it later. Topic 10, long-term durability, archaeological analogues. This will be developed in our session dealing with ferrosilates and archaeology, because it is the system. Topic 15, material for radioactive waste, particles, and gas pollution. I found some interesting papers that I want to share with you. Geopolymer technology for the solidification in simulated ion exchange resin with radionuclides. This is from Taiwan. In this study, geopolymer was applied to convert ion exchange resins contaminated with radionuclides into a solid waste form. Geopolymer has superior properties to enable the encapsulation of spent resins. The International Atomic Energy Agency, that is in Wien, has reported that geopolymer can be used for the stabilization of radioactive waste with a geopolymer cement matrix and provides excellent leach resistance. Therefore, slag-based geopolymer was studied for the purpose of spent resin solidification in this study. And then this one, which is different, also coming from China, from the group of Professor Kuhn Min Kui. We will have one of the students, not here, but another, that will present what this group is doing. A porous gradient geopolymer-based tube membrane with high particle materials removal rate for air pollution. Existing technology does not meet the urgent need for a cheap and efficient carbon particulate matter, PM, particle size below 10 to 2.5 nanomicron. These are the particles removal. A porous gradient geopolymer-based tube membrane was successfully prepared using one-step moldings. Many diseases and conditions have been reported to be associated with particle materials pollution, especially from the industry and the cars, including lung cancer, asthma, morbidity, and mortality. Recently, people in developing countries, such as China, have suffered from serious particle materials. The innovative porous gradient tube membrane for PM removal was fabricated by metakaolin-based geopolymer with a 70 micron porous membrane body of 0.1 micromillimeter or 100 nanoporous surface. The porous gradient geopolymer-based tube membrane has a compressive strength of 3.9 MPa and a pressure drop of 0. MPa, so it works. So this is the membrane here, 0.1 micrometers, 100 nano, the particles here, and they go through. In PM filtration, the removal efficiency reached 98.5% to 99.3%, showing great potential for geopolymer in particle materials removal filtration. So the scientists are working on how to cope with the pollutions in these big cities, in Beijing and the like. And the solution is geopolymer chemistry. Fourth part, geopolymer cement and concrete. The first geopolymer cement was invented in 1984, that is 35 years ago. I have been hired by what was at that time the major Portland cement manufacturer in the Western Hemisphere, that is in America, Lone Star Industries. We there, with James Sawyer, developed the first geopolymer cement, that is metakaolin slag-based geopolymer, filed in 1984, published in 1985, early high-strength mineral polymer. At that time, we didn't use the word cement and concrete, it came afterwards. For this invention, our team received one of the highest award, a Golden Ribbon Award, by the National Association for Science, Technology and Society, that was delivered in Washington, D.C., in the US, in 1994. So we started in 1984, slag MK-based geopolymer cement, and we worked on the way of improving this cement. That is, by improving it from the raw materials point of view, to have a more and more efficient material. 1997, invention of the slag rock-based geopolymer cement. 2006, invention of the slag fly ash-based geopolymer cement. 2010, invention of the slag ferro-based geopolymer cement. If we compare the energy needed for making a Portland cement, 1 ton, we need 4,700 megajoule per ton. For a rock-based geopolymer, we need 9,960, and for fly ash-based, 775 megajoule, which is a reduction by 60 to 84%. If we compare the CO2 emission, Portland 0.85 ton per ton of clinker, geopolymer 0.1 to 0.15, which is a reduction of 80 to 90%. These are tremendous numbers. And several scientists affiliated to the Portland cement industry tried to counter these numbers and published wrong geopolymer low CO2 calculations. They, from my point of view, published false CO2 emissions because they simply based all their calculations to the first invention. They did not follow the development that have been made by ourselves or by the industry. So they took the first numbers, which means 50% of silicates, high amount of CO2 emission, low amount, and just compared it to Portland. I made official rebuttals in several papers, and this rebuttal is very strong. These scientific papers that is in our Geopolymer library or published in the internet with Elsevier's materials today in order to clarify the situations. What we have developed is the following. The evolution, at the beginning we had 50% potassium silicate in our first geopolymer cement. This is the polymer cement in 1984. In 1987, this is another material, still 50%. In 1997, rock-based, we decreased the use of K silicate and came to 20%. but we achieved super high strength. In 2002, we just got 50 MPa, but we had only 17%. So we dropped from 50 to 70% of potassium silicate. In 2006, the fly ash based is only 14% sodium silicate, potassium silicate, to reach 10 MPa, 10% if we want only 40 MPa. But these figures were not taken into account by the opposition. When this first public buildings has been introduced, and when the airport was made, then the Portland cement industry lobby started to react. And they react in the following way. There's been mandated by the United Nations Environment Program to present their view of eco-efficient cement, potential economically viable solutions for low CO2 cement-based materials industry. And they had the following authors: Karine Scrivener. She is professor at the École Polytechnique Fédérale de Lausanne, but in fact she had been scientific advisor by the big cement company Lafarge. This one not, but this one yes. Elise Gantner, former scientific director from Lafarge. And they wrote a paper officially for United Nations, how to reduce the huge emissions of Portland cement industry. And they claim, well, we can reach 10%, we can reach 20%, and so we can reach maybe 30%. And they also talk about geopolymer cement. Final remarks. Geopolymer materials produced with fly ash and blast furnace slag have low CO2 footprint, but their mitigation potential is dubious, since they will mostly divert slag and fly ash from Portland cement. In other words, in order to cut the CO2 emission by 20% for the Portland cement industry, they will use all slag or fly ash available. And they want to do this provided the geopolymer cement is not developed, because the geopolymer cement can use the slag and the fly ash more efficiently, and we can cut down up to 80%. So they want to forbid the free selling of slag and fly ash. This is their purpose. And this has been the situation before we developed the geopolymer cement. It was impossible, practically in Europe, to get blast furnace slag 15 years ago. It was in the hand of the cement industry that has agreements with the steel industry. And same for fly ash. And they want to go back to that system, but it is too late, because the steel industry understood that what they are making slag is no longer a waste, but it is a byproduct with a high value. And they have created their special companies that are selling, marketing slag and so forth. But you see the difference, and you see why it is so hard to develop the applications, even if it is the best solution in order to save the world. But they don't care. The lobby is here, and the official United Nations is not aware of what we are doing, or is in fact accepting the judgment of this study that has been presented. So we have now several suppliers for metakaolins, so this is free. We have suppliers of blast furnace slag. We worked with ArcelorMittal in France to show what to do with the slag and geopolymer cement. And this is too late for the Portland cement. But this is what they want to do. So you must be aware of that position. From the geopolymer cement concrete, we have practically solved all the parameters studied: adjuvant, plasticizers, water reducers, retarders, drying shrinkage, user-friendly one-part GP cement. The problem is that all these knowledge has been developed with partners, and they are proprietary, and today we cannot talk freely about them. So you have to ask the representative of the industry here that are here, and in order to give you some advices. I can only give you some hints. There are products that are working. There is a list, but there is not one product working for geopolymer cement, because each batch is different, and it has to be, there is no real one for general applications. So far, we are not so far from this system, but it has been solved individually. In 2013, I published a review on what was my thinking about the development of geopolymer cement, and I wrote the following. In the 2012 State of the Geopolymer R&D, I suggested to select two categories, namely slag fly ash-based geopolymer cement. Fly ashes are available in the major emerging countries, but the problem is normally there should be less and less fly ash, since in terms of CO2 emission, coal should be banished for the producing of electricity. So we have to go back to geology. And for geology, this is the ferrosilate-based geopolymer cement. This geological iron-rich raw material is present in all countries throughout the world. It is based on the molecule ferrosilate, FaSiOAl. It results from the geopolymerization of geological elements that are rich in iron oxides and ferrokaolinate, and it is formed in weathered acidic rocks, sandstone, granite, and gneiss, or basic rock, basalt, and gabbro, and we have a special session on this topic later. Worldwide availability, you'll find the material everywhere. And in terms of durability, you have an example at Pumapunku, at least 14,000 years old. So for those who are asking what is the long-term durability of geopolymer concrete, geopolymer cement, look at this one. This has been my state of the geopolymer for this year. Thank you.